Hello, everyone. So, last time on PChem, we were talking about how we can use our atomic orbitals to build up our molecular orbitals. And part of this was taking our atomic orbital energies and turning them into molecular orbital energies. But one of the real problems of that is just the sheer fact that we need to actually determine our atomic orbital energy values. So these were our Coulombic integrals. So if I have a diatomic, I've got two values, one for atom A and one for atom B. So there's many different approaches that we can try and use to uh, build up our Coulombic integral values or our orbital energies. The classic approach for theorists like me is to try and calculate them directly. But as you've seen previously, that can be quite problematic, as oftentimes when we generate our orbital energies, we're making some sort of severe approximation, such as using z-effectives or some other neglect of true electronic-electron interactions. Another classic approach is the idea that we can steal from Koopman's theorem and use our ionization energies. So if I have the ionization energy of my electron, this is going to tell me exactly how far down into the potential well the electron exists. However, there is a slight problem with that, is that when I'm looking at the electronic energies of an orbital, in terms of its ability to make a bond, I don't care about just how hard it is to remove that electron. I also care about how readily it accepts an electron. So one of the major approximations we can do is saying that I'm not going to just care about the ionization energy, I'm also going to care about the electron affinity. So the true orbital energy can be thought of to a certain extent as an average of the ability of the electron to leave and the ability of the atom to collect a different electron. So one way to think about it is that while my actual orbital may be somewhere down here, can gain or lose an electron, it more effectively acts at some intermediate point. So when I'm trying to use an orbital energy to describe bond formation, it may be more accurate to describe my Coulombic integral as somewhere around the halfway point of the ionization and electron affinity. And one of the reasons why this is actually quite useful is this is more of a description of how much an atom wants that electron. And that's going to be very important in bonding, in both that it describes how readily will it want to grab another electron and how much does it dislike losing an electron. For example, if I'm looking at something like neon, it's not going to want to lose an electron at all, but nor does it want to gain an electron. And so this will modify its orbital energies effectively, which is going to be important because while it won't ionize, it's also not going to make a bond. Now, as you may have noticed, this description of how much an atom wants an electron is going to sound vaguely familiar. And that's because it turns out that this idea of our Coulombic integral is actually very related to our good old friend electronegativity. So this is one of the major reasons why I took this particular atomic trend and pushed it back a little bit, because electronegativity is actually a very good description of atomic orbital energies as they refer to as bonding. So in fact, it turns out that this particular definition or approximation of our orbital energies looks rather like one of the major form descriptors of electronegativity, specifically what's called Mulliken Electronegativity, which literally just is the fact that you'll take the average of your ionization and electron affinity in EV, and congratulations, that's your Mulliken electronegativity. So as you may have noticed, this is literally just the negative of our Coulombic integral. So this is actually really useful. But what it also ends up doing is it shows very much that the energy of our valence atomic orbital, so our atomic orbital that is going to be involved in bonding is going to be tightly linked to our electronegativity. The more electronegative an element is, essentially the lower in energy our orbitals are. So this actually helps explain a lot of ideas of electronegativity. The reason why an atom wants an electron is because it has an unfilled orbital that can participate in bonding that's fairly low down energetically. And that's really what we're kind of describing with both electronegativity and Coulombic integrals. So we can make use of both of these fairly well. And so really what we're talking about when I'm looking at either Coulombic Coulombic integrals or electronegativity is all I'm caring about is the desire of an atom to essentially obtain an additional electron or not lose the one it has. So this is essentially what pull uh, an atom will have on a pair of electrons, not just the single one that ionization or electron affinity alone kind of describes. However, one of the things you should watch out for is this Mulliken definition of electronegativity is quite similar to our Coulombic integral. It turns out that when most people are talking about electronegativity, instead they make use of an older definition called Pauling electronegativity. And these are actually substantially different. So the idea of the Pauling electronegativity is simply focusing on this idea of electronegativity being the desire of an atom to procure electrons. So how much does it want the electrons in a bond? And so what it does is it first starts by defining some reference atom and defines that electronegativity. So according to the Pauling definition, hydrogen, because it's about the most abundant atom we have, and it turns out that it bonds to everything, is going to be our reference case. So the Pauling electronegativity of hydrogen is 2.2. All other electronegativities are going to be taken with respect to hydrogen. So if an atom is more likely to steal electrons from hydrogen, it would be considered having a greater pull, more electronegative. If hydrogen wants to steal electrons more from another atom, then we go ahead and again use the difference of how much it's stealing those electrons. And it turns out that you can actually tell the difference in between the electronegativity of two different atoms by making use of bond dissociation energy. So I apologize, this is a little bit of a callback to last semester, but the idea is I have two atoms, say hydrogen and chlorine, and I can take the difference in between the electronegativity of these two atoms using the square root of pretty much the differences of their bond dissociation energies. So I have to have the bond dissociation energy of the combined species. So if you're looking at hydrogen and chlorine, HCl, hydrogen and carbon, you're looking at an HC bond. And then you're saying, okay, this is how much energy it takes to break that combined bond. I'm going to subtract out the average of the energy it takes to break each of the individual bonds. So how much energy does it take to break a hydrogen-hydrogen bond? How much energy does it take to break a chlorine-chlorine bond? Take the average of these two, and then the difference. So again, the idea, if the bond of the mixed species has the same energy of the average of the bond of the two combined species, then it means that the electronegativities are very similar. They behave like each other. Or in our in our newer perspective, it means that our orbital energies are likely very similar, so that they line up fairly well. The more different these two guys are, it'll tend to drive a greater difference in between the average and our combined species. And then this leads to a greater difference in electronegativities. So let's actually work the numbers for an example case. So who doesn't love HCl, our favorite diatomic acid? So you can go ahead, go into the back of your book and find the energies for H2, which is going to be our AA species, the bond dissociation energy for chlorine, so that would be our BB, and then the bond dissociation energy for the mixed species. And then here's the trick. We're going to go ahead and put in a reference value of 2.2 for hydrogen. Again, this one comes straight from definition. If you're looking at a species that doesn't involve hydrogen, you will have had to already determine the electronegativity of that species. So again, this method entirely focuses on the difference of electronegativities. So plugging in all of these values, we find the difference in electronegativities between chlorine and hydrogen is going to be roughly 0.98. Now, if you're really careful and you're tracking the units, you'll technically realize that this has very weird units of square root of EV. As a result, most people tend not to report units on electronegativity. But again, here's the rub. I just know that chlorine and hydrogen differ in electronegativity by roughly 1. Now, here's where you have to use your chemical intuition or your classic Gen Chem knowledge. We have to figure out who's the more electronegative element. So we can use the guiding rule that the further right in the periodic table I go, the more electronegative I tend to be. So as a result, chlorine's probably the more electronegative element. So that means that I'm going to have a net electronegativity for chlorine of 3.2 and not 1.2. Watch out. This method does prove that chemical intuition can be fairly important. So again, it is worth noting that one of the major reasons why Pauling electronegativity tends to use this square root is to try and bring all of the values into a much shorter range than we see in, say, the Mulliken electronegativity. So again, Pauling electronegativities tend to bottom up somewhere around 0.8 or 1 and tops out with fluorine at about 4. So what we can end up doing is, again, making use of these electronegativities to tell us a lot about orbital energies. Now, where this can be slightly problematic is I may have, say, calculated my Pauling electronegativity for hydrogen and chlorine, but it turns out what I actually care about is Mulliken electronegativity, because that's going to be the one that will give me my Coulombic integral that I started this whole process wanting to determine. So it turns out that while these two methods are not identical, we can actually convert in between the Pauling and the Mulliken electronegativities. Now, it is worth noting that this relationship is not perfect. It is a good general trend. So if you're looking for numerical accuracy, you're probably going to actually want to find the literature numbers and calculate each one independently. But if you're looking for some rough values, this is actually not the worst place to start. So you can take your Mulliken electronegativity, then square root it down to bring it down to the same scaling and units as Pauling, multiply it a little bit, and then recenter it around that hydrogen value of 2.2, which is what this minus term comes in. But here was actually kind of the issue, that we just determined the Pauling electronegativity, and what I care about in our case as physical chemists is going to be the Mulliken. So in this case, sometimes it's useful to be able to rearrange this equation to solve for Mulliken in terms of Pauling. It's a little bit more of a expanded form, mostly due to this squared term, but it's still a fairly straightforward relationship. So using our value of 3.2, we can plug that into our Mulliken expression, and what we end up finding is that Mulliken has an electronegativity, and the Mulliken basis, we have an electronegativity of roughly 11.46, or if I want to think about it in terms of energy, 11.46 eV. Now, where this is actually really useful is that this also feeds back into my Coulombic integral, because what this tells us is that the Coulombic integral for chlorine is negative 11.46. So this means that the energy for the chlorine atomic orbital that's involved in bonding is actually fairly low in energy, or fairly stable, which is one of the reasons we tend to describe chlorine as an electronegative element. So again, one of the reasons I wanted to take this little bit of an aside into electronegativity is to show that electronegativity gives us an additional ability to look at the stability of atomic orbitals and will help give us some insight as we proceed into how these orbital affinities for electrons can play a significant role in making molecular bonds. So we'll go ahead and return to these ideas a little bit later, as next time we start to uh, use our electronegativities and what we've learned about determining MO energies to bring it together and talk about a real system. Next time, hydrofluoric acid. Till then, take care and stay healthy.